Okay. Then, yeah, let's go and see how it is organized this short hike through Adaptive AUTOSAR. So first, let's discover why do we need AUTOSAR and more specific Adaptive AUTOSAR. Then we will find out the main attributes of Adaptive AUTOSAR platform, main steps to create, configure, build, install, test, deploy one adaptive application using an adaptive platform integrated with an adaptive IDE are described further. Then we could go and see how to create, configure, build, install, and deploy one adaptive application, what information is inside different manifest files, and in the last part we describe what contains an adaptive platform product line and how could be used to create, configure, build, install, deploy, and test one adaptive application. Yeah. So first, let's see why do we need an Adaptive AUTOSAR platform. Yeah. So let's take, for example, we have several applications, 1, 2, and 3. These applications are installed in 3 hardware systems, different hardware systems, but for example, we need, for example, to install them in other hardware systems, and we will face some adaptations issues because we need to modify our software in order to could run in another hardware system. Then we will face huge issues and huge effort in order to adapt this software to run in a different ECU, different controller. That's why this AUTOSAR standard was created. In fact, AUTOSAR stands for Automotive Open System Architecture, which is a layered architecture, as could we see here in the right. It was created by a consortium of companies where as creators of this consortium were BMW, Bosch, Daimler, Continental, Volkswagen, PSA, Toyota, and so on. And this AUTOSAR platform, firstly created in 2003, a classical one, classic AUTOSAR standard, was organized in layers, and it was intended to abstract the hardware layer, so the applications creators could use their applications to be installed in different hardware with minimum effort. Yeah. So for example, we have here into the right 3 kinds of applications, and they are using our this classic platform. Yeah. Inside this classic platform, we have, for example, the hardware and then an operating system. And besides this, above this operating system, we have several layers, for example, microcontroller abstraction layer, then an ECU abstraction layer, and then a runtime environment. These layers are intended to hide the hardware implementation towards these applications. So these applications use some APIs provided by this platform and make them independent of the hardware where they will be installed. Okay? And then let's go further and see why do we need an Adaptive AUTOSAR. Well, after 20 years of classic platform usage, some new market requirements occur. For example, this electromobility, which is intended, for example, in 2035, the largest automotive markets will be electric, and then we need some different requirements to be taken into consideration in comparison with the classical platform. For example, for automatic driving, for autonomous driving, we need to process large volumes of data, big chunks of data, and also to run complex algorithms. And for this, the classic platform is not appropriate to be used. Also, we need to implement some fail operational systems that could handle the errors during the usage of our platform to be corrected and to be restarted and to not to solve the different errors who could occur during the usage of our platform. Of course, for this adaptive platform, we need also a service-oriented architecture, which is different comparing to the previous protocols used in classic AUTOSAR like CAN and FlexRay. Also, we need to implement some requirements concerning vehicle to everything technology. Then our vehicle will communicate to other vehicles, to other systems outside the vehicle. For example, some servers from cloud system. And also we need to implement an over-the-air update system. Then could allow us to update the software versions installed in our car. Yeah. And then, of course, the real revolution in automotive concerns different aspects of the car systems. For example, from the head unit display, which was installed and deployed in several million of cars some years ago, we will have nowadays some multi-graphic displays, and in the future we could have, for example, some future infotainment features which could allow us to install, for example, and subscribe to Netflix, to Spotify. Of course, these systems, infotainment systems, could be used when the car is not in motion, for example, in a traffic jam. We could evolve also the autonomous driving level from level 1 to level 3, when we could assist our car for example, braking systems, or also to detect the traffic lanes, and to automatic parking systems could be implemented. And of course, the car architecture will evolve from distributed system to some zonal architecture, where central high-performance controller could be used, and also some domain controllers could be installed, like it is seen in this column of architecture. And of course, the engine of our car could be evolved from diesel engine to hybrid platform, and to, of course, electrical platform. Okay? And then, of course, the car architectures will evolve to the usage of high-performance controllers, which become simpler and more efficient. For example, in our diagram here into the right, we could see that we have a central gateway installed and deployed into a high-performance controller, which could interface head unit display together with some infotainment features into the left. And below we could have several ECUs installed and deployed into some several virtual machines installed here in another high-performance controller. And of course, we have some interfaces to some input-output controllers using some classical platforms into some classical ECUs, controlling some basic functions and features of our car. And above you could see a smart antenna connecting our software system from our car to a cloud architecture and to a cloud server, and allowing us, for example, to exchange information to other vehicles, to other servers, and allowing us, for example, to perform software updates and, of course, application updates. And then here we could see, for example, that before we could have several ECUs where we have running several types of operating systems with several types of platforms, classical ones or adaptive ones, and these 3 or more ECUs could be, for example, replaced by a high-performance controller where we could configure several virtual machines which will replace our ECUs, and in each virtual machine we could install a specific operating system. For example, for adaptive platform we could use some Linux-like operating systems, Linux, QNX or Android. and for classical ones could be, for example, OSEC. And these virtual machines could be managed by a hypervisor, a microkernel hypervisor, together with some virtual Ethernet switches. Yeah. And below we have, of course, the hardware from our high-performance controller board. And then let's take a short look and talk about the main attributes of an adaptive AUTOSAR platform. Yeah. So we, for example, the preferred language for our adaptive AUTOSAR platform is C++. And why? Because this kind of language, programming language, is scalable, and it allows us to manage a big bunch of data. Also, it is very configurable, and if we, for example, use C++ 14, which is specified, the rules, the programming rules are specified into this AUTOSAR requirements and guidelines PDF file from AUTOSAR website, then we could apply new features concerning C++ 14, for example, smart pointers or other important features of C++ 14. And also it gives us total control for memory management and access to low-level programming. And of course, we could use a POSIX compliant, a Linux-like programming language, which have, for example, basic features like, for example, shell scripts, and also signals processing, process management, and also pipes, inter-process communication, for example, shared memory, also segmentation and interruptions management, and so on. Okay. And then another characteristic, of course, it is the usage of service-oriented architecture. Mainly, this architecture, it uses, for example, specific protocols like DDS or SAM-IP. In our case, SAM-IP was chosen in adaptive platform in general, and mainly it consists in a service registry, which is implemented in COM Manager, which is part of of the adaptive platform. This service registry manages the communication between two applications. For example, in our case, a service requester, which is a client which requests some information or some data, and the service provider, a server, which provides some informations. And service provider subscribes its informations to the service registry, and service requester requests to the service registry some ID, and if it finds this ID of this interface deployment, then the communication could take place, and the exchange of the information could take place between the two applications. The benefit of this SAM-IP protocol it is that it hides the transport protocol and all the data concerning the communication. Like that, for example, the applications designers could increase their effort and could create their applications without dealing with other additional information like communications, parameters, and so on. Yeah. So the main principles of service-oriented architecture is standardized service contract, loose coupling, abstraction, because it abstracts the transport layer, autonomy and reusability. The main disadvantage could be, for example, the high overhead and high investment, because you need to configure a lot of parameters in order to set up the two applications in order to communicate to each other. Yeah. And of course, the usage automotive grade Ethernet is by default choosing, because we need an extremely high big data exchange, so we cannot use the previous protocols like FlexRay and CAN or MOST, because we need at least 10 to 100 megabits per second, maybe 1 gigabit per second. And specifically to automotive grade Ethernet, comparing to a normal Ethernet, it is the usage of only one pair of twisted wires, excepting for diagnostic dual IP protocol, where we are forced to use two pairs. Yeah. Then let's take a short look here and see the main differences between the two types of platforms, of AUTOSAR platforms. Classic platforms, which was created the main specifications were created some 20 years ago, and adaptive platform utilized since 2017. So as you can see, adaptive platform uses a POSIX-like operating system. As for classical platform, we use some OSEC OS based, some real-time operating system. Concerning the programming language, C++ is the language of choice for adaptive platform, allowing us to perform complex algorithms and processing a big bunch of data, and C programming language for classic platform, and so on. And also we could see that the code is executed directly from read-only memory for classic platform, and in adaptive platform we could see that the applications are uploaded into a RAM, and then they are executed from there on its own address space. Yeah. The communication, of course, it uses some CAN, FlexRay specific protocols in classic platform, as comparing for adaptive platform we use some IP and service-oriented communication, some IP protocol. Yeah. Okay. Then let's talk a little bit about main use cases and work products for an adaptive AUTOSAR platform. And here, this adaptive platform methodology it is an important document that describes main use cases together with some input artifacts which are used in our use cases. And then, of course, in this document, there are some work products specified for each use case. And for example, as output artifacts could be, for example, IRXML files, which are some AUTOSAR XML specific protocol in which our data is created in order to be used in our platform. Some source code, some object code could be some output artifacts, and even test files and configuration files. For example, JSON or YAML format. It depends on the implementation. Yeah. Of course, there are some new terms in Adaptive AUTOSAR platform which are already used now. For example, machine, which is replacing the ECU, because in our case could be a virtual machine where the software is running. Software packages, which are containing the binaries of our applications, and of course the configuration files, which are obtained from the manifest files. And of course instances of our adaptive applications, which are processed in Linux POSIX-like operating systems. Yeah. Then we have several phases in order to create an adaptive applications. We start with an analysis. So the analysis is needed for the options to be chosen for the adaptive system to be built, and of course in order to check the timing constraints between the sensor and actuators of a feature. In our standard there are no specifications concerning this step. Yeah. And then here we could have an example of how to build function architectures. We could have, for example, 5 functionalities, A, B, C, and D. And these functionalities could englobe either classical aspects or adaptive aspects. So in order to implement this kind of functionalities, we need to separate and to split these functionalities in different applications. Some of these applications could be adaptive ones, like for example here API 1, API 5. Some other applications could be software components, like they are named into the classical world, like SWC 2, 3, and 4. And of course, we need to specify the communication channels between different functionalities, and later on from this function architecture, we could get some common software architecture where we could see that, for example, API 1 from adaptive application communicates to a classical one, SWC3, and SWC2 from a classical component, it communicates with SWC4. Yeah? And then later on, we could, from this common software architecture, we could set up different views. For example, a classical view here where we could illustrate, for example, a virtual function bus view where our classical application communicates to each other. And of course, we could set up another adaptive platform, classical platform mixed view where we could have, for example, an adaptive application communicating with a classical one. Yeah? And then in the last phase, we could map our applications to our hardware or virtual machine in the adaptive application case. For example, the two applications from adaptive will be running into the machine 1, and then they will, this machine 1 will be installed into the ECU1 as a hardware, and the SWC 2 and 3, for example, could be installed in the ECU2, and the last application from the classical platform is WC4 could be installed in a third ECU, ECU3. Yeah? And then let's take a look at how and illustrate how to generate a software package concerning an adaptive application. We could start to create, for example, an IRXML file, service interface description, where we could specify how our application will communicate to another application using different types of communication. For example, could be used methods, events, or fields. And of course, we need to specify the data used in these methods, events, or fields. And then from this service interface description, we run a code generator, and we get some header files, a generated code. This generated code will be linked to our implemented code. We need to, of course, to write our application's source code, header files, and CPP files, where we could have access to some APIs from our adaptive platform, concerning, for example, different features like communication, persistency, or time synchronization, and so on. Maybe also health manager. And when we are ready with our source code, I mean, we have tested it, we could try to solve our compiling issues, and we could start to run and build and to link our adaptive applications. In our case, you could see here 3 applications, APP1 proxy, APP2 proxy, and APP3 skeleton. The first 2 are client applications, and the last one, skeleton, it is a service application which provides some services, and our clients consume these informations provided by our skeleton, by our service application, by using either IPC communication, if our applications are deployed into the same virtual machine, I mean the same ECU, or some IP protocol where our applications lies in different virtual machines, so the communications is performing between two different machines, so they are installed in different places. Yeah. Then here we could have a short diagram from our methodology document from the website of AUTOSAR Consortium concerning Adaptive AUTOSAR with different stages in order to create, test, install, deploy, and run an adaptive application. Like you already see, we start with developing a service interface description where we need to define the data types, could be, for example, integers, strings, even complex types like maps or structures or so on, vectors. And also we need to configure the events, methods, or fields, types of communication, and then we generate the source code, the header files. Then in parallel we could start to develop our source code for adaptive applications, the second step. The third step, we could also need to develop some platform level applications like, for example, UCM master used to update our software, yeah, versions or applications, or maybe also some functional clusters from our application. Then we need to integrate our software, I mean, together with some APIs from some functional clusters libraries or some Linux libraries. Then, of course, we need to select our operating system distribution, could be Linux, QNX, or maybe even Android. We need to configure and define our machine, our virtual machine, I mean the parameters for our machine. Could be, for example, the states, machine states, also some function group states could be configured in order to synchronize our application with other applications if there is a case of this kind of synchronization. Then we need to create some applications, manifest, we will talk about this later on. Then we need to define and configure servers instance manifests, which are used together with some IP protocol to communicate, to set up a communication between two applications which are lying in two different virtual machines. Yeah? And then, of course, to set up the machine, and then later on to deploy our software package into our to the adaptive platform. Yeah. And here there is another diagram which is describing the flow of our adaptive application creation, from creating the source code, choosing the data types, until the deployment of our application. We, for example, start to define the services, creating the service interface description .xml file. When we start to develop the software, source code application, yeah, adaptive application, we generate our header files using as an input our XML file. Then in parallel we start to develop the platform and configure the machine, and we get the machine manifest file, yeah, and this manifest file will be deployed later on our platform, yeah, and then yeah, also the machine manifest file and service interface description are used as an input to create the service instance manifest used to set up some IP communication if it is the case, yeah. And like that we get the software package components. For example, we get the executable by using the compiler and the linker, yeah. We have the binaries, and then also the application manifest and the service instance manifest, and all this package will be deployed into the adaptive platform using the update and communication manager functional cluster. And of course, these files will be deployed into spaces, a binary folder, and of course a data folder where our configuration files will be used either by the platform by adaptive application or by the daemons which are running on the adaptive platform. As you can see here, the processes, adaptive application processes, will be triggered by the execution manager together with operating system, and also some APIs will be used by our adaptive application, either from execution manager, from operating system, or from other functional clusters. For example, could be time synchronization, could be health manager or persistency manager. It depends on how our application is written and what functionality is implemented in our application. Yeah? Okay, then let's talk about modeling and how we should configure the manifest and design the application. What are the different types of the manifest files? And in fact, what is the definition of a manifest item? Yeah. And here we could see that the manifest, according to the AUTOSAR consortium, it is a piece of AUTOSAR model description. So that is created to support the configuration of an AUTOSAR adaptive platform product, and which is adapted to the AUTOSAR adaptive platform, uploaded to adaptive platform product. Yeah. A manifest file could be implemented in one or several files. It depends on the implementation platform. Yeah. Could be, for example, a service interface description. We already talked about it. And this service interface description file uses as input some data types, and it is used, for example, to set up the communication between two applications. Could be either to set up an IPC communication where the applications are into the same virtual machine, or to set up a distant communication where, for example, our applications are installed in different virtual machines. Yeah? We could have also a service instance manifest file, which is created in order to be used to set up some IP communication between two applications lying into different virtual machines. Yeah? And this service instance manifest has three types of data. Service interface deployment, where, for example, we set up some IDs to our events, methods, or fields in order to identify them uniquely. And then, of course, our service interface deployment also has an ID. Then, of course, an interface deployment could have several instances, and we also need to set up an instance ID, service instance deployment ID, and this service instance deployment ID, we need to map it to a machine. Yeah? And our machine, also, of course, has all the parameters specific to our machine, for example, an Ethernet address and so on, port and so on. Yeah, like that, our information concerning the transport layer is hidden against the application data and source code. Yeah? And the application creator could handle and deal only with application source code. And the integrator could set up this kind of manifest files. Of course, we need to set up an execution manifest where we could set up the dependencies between different applications and between different clusters which are used by our application. Which this information used, of course, during the startup and shutdown of the adaptive platform. Of course, we need to set up a machine manifest where we need to set up the network connection, the machine states, and if it is the case, some function group and some function group states which are used, for example, to synchronize some process states, if it is the case for our processes or adaptive applications to be synchronized in some cases. Yeah? Then here, the modeling, in fact, comparing to the methodology, is describing us, is providing us how our application is our adaptive application is configured in order to be deployed, successfully deployed and run into our adaptive platform. We could see here that we set up an application. We need also the service interface description, some data types used, and of course, some service and client software components. We talk already about execution manifest, machine manifest, and concerning, of course, a service instance manifest, which is used during setup of some IP communication. Yeah. Then let's talk about what is inside an adaptive platform product line. And here we could see that we have upper layer where we have the adaptive applications, which are using some APIs provided by platform foundation functional clusters. Our platform foundation functional clusters are on the left side, which are colored in blue into the layer there, and in the functional cluster with gray are platform service functional clusters. And let's talk about each functionality of each functional cluster. Yeah. Below we could have virtual machine, of course, some containers or hardware, and of course some operating system. Yeah. For example, let's talk about the COM manager, which is on the left. Normally it is implementing the SAM IP communication protocol, which is used between two applications which are lying on two different machines, or could use the inter-process communication, mainly maybe shared memory, where the application is performed locally between two applications lying into the same virtual machine. Of course, for the persistency features, we use the persistency cluster. Two types of read-write memory access could be used. File proxy, which could be used for one or several files. It is used, for example, for software updates together with update and configuration manager during the software updates. And file key value storage is used for read-write of some specific data of adaptive applications. Each adaptive application has its space and its database of their data, of its data. And also we could see another time synchronization functional cluster, which is providing some time-based resources and some APIs which is dealing with time synchronization features. Health manager, which is implementing and providing some APIs to the adaptive applications for the logical supervision, for deadline supervision, for a live supervision. Of course, if something goes wrong with our health platform, it triggers some actions, for example, restart the application or restart even the platform. Yeah. Identity and access manager, it deals with the access of our applications to some services according to some rights of authentication and identity. Diagnostic and logging tracing, it provides for each adaptive application, of course, and for other clusters, some logging information. Concerning the state manager, performs some state management together with execution manager. It requests the transition of our adaptive application in different states or function group states by requesting this to execution manager. Of course, the execution manager, which is a platform foundation functional clusters, it deals with startup and shutdown of our platform adaptive applications, but also the functional clusters. Update and configuration manager, it deals with the software updates, installing the applications, and also roll back some applications updates in case if our software update goes wrong. Yeah. For example, some corrupted files could be met, and the check of this package is wrong. then the rollback is performed. Yeah. And of course, we have a diagnostic functional cluster, which is dealing with diagnostic features like in the classical platform. Yeah. And the network manager, which is dealing with the transition from the normal state of our physical platform to the bus sleep mode in order to have an efficient energy consumption when the communication between different nodes of our network system it is not used. Yeah. Then we have a typical architecture here using a mix of adaptive and classical platforms. Into the left part we have several virtual machines with several operating systems, like for example here in yellow Linux operating system or Unix one, if it is the case for adaptive platforms. And also we have the adaptive modules, these ones from here, yeah, so our adaptive platform, yeah. And then into the red color we have the classical platform using an OSEC, for example, OSEC operating system with some classical components and of course some classic applications. A security virtual machine also it is illustrated here, and also a safety virtual machine using a classical platform. Into the right part we have some tools, some IDEs, integrated development environment. The red ones are used, for example, for classical platform, and the adaptive one are illustrated in the yellow color. Yeah, and they are used either for application development, but also for integration and the deployment actions. Yeah, of course for logging and debugging. And all these virtual machines are managed by a hypervisor and installed into our high performance controller. Yeah. And then we could see here, for example, for our integrated development environment, we could have, for example, some development application features, like for example, to create a modifying application, for example, to create and read the source code. We have an editor there. We have also a compiler, a linker, and also even a debugger. We could also debug our application into the target. The target could be an emulator or a physical board. Also, we can test it using either unit tests, and later on we could also use functional tests, yeah, to run and debug our application directly on the target. And of course we could visualize our test result and also to take some decision if there are some wrong or not okay tests. Yeah. And the second part of our features concern the integration part, integration and deployment. Yeah. We could set up and configure some configuration files. Some manifest files could be created here, and then later on by running some generators we could get the configuration files in some JSON format, and like that together with our built application, so our binaries, we could deploy our software package into our target. Could be a QEMU, a quick emulator, or a physical board, for example S32G physical board, or ARM board, or H3, M3. It depends on the chosen hardware. Yeah. Then, where to get help? If you need help, you could, for example, go to the AUTOSAR consortium page, autosar.org, or could go, for example, either to YouTube. There are several presentations there from different providers, adaptive platform providers, or to different websites of different platform providers, like for example Vector, Electrobit, KP, Theta, Siemens, and so on. And if you have questions, we will set up some short session of question and answer, and of course we will not podcast, and in this podcast we try to answer all the questions. One question, for example, is how the source code is generated from XML files. There are some parsers, and it depends on the implementation which is chosen by different application providers. Platform providers could be, for example, written in Python or in C++, it depends, or in Java. And the source code is generated from an XML file, and for example, generates some header files which is providing some information file, some header files concerning the instance IDs which are put inside these header files together with some namespaces and together with some specific C++ programming instructions. Yeah. Which containers are used in Adaptive AUTOSAR development? Could be, for example, Docker containers, could be runC containers. It depends on what solution is chosen by the adaptive platform provider. The main advantage of using the containers, it is that it is an isolated environment where our application could run, and of course we could set up a bunch of, for example, tools and software applications and libraries which could be used isolated from other environment, for example from our adaptive platform or from our application, and like that our application is secure also. Concerning security features is much more isolated than if it runs on a plain system. Yeah. For example, in QNX, as far as I know, there are no containers implemented. And as cybersecurity is a critical concern in the automotive system, how does the adaptive platform AUTOSAR address the challenges of security software in a connected system? Well, we need to set up, of course, complex systems, for example, to encrypt our information and to encrypt it and to put and store it into our database. So using the encryption, it was one of the case. Of course, using some firewalls, but it is, as far as I know, it is still under development in some adaptive platform providers. Yeah. For the other questions, I maybe will answer later on the podcast activity. Yeah. And thanks a lot for your attendance, and have a good afternoon and a nice afternoon, and hope the information I was provided to you were useful for you, and thanks a lot, and see you soon. Bye bye.